Yeah. There we go. Thank you.
Yes, I was going to say. Get your approval.
Oh, people don't normally sit on that. But I guess.
But she did. I mean.
I know, I don't. Yeah, I mean, it's less relevant.
Okay, I'll take it.
But otherwise, yeah, that's fine. I'm happy with what to do. I take inspiration from lessons and Leslie's not robots.
Yes, Leslie doesn't need that.
I know.
Okay, so we have.
And I don't know if this mic, I'm connected on a mic. I don't know if it's working. It might not be necessary.
So keep.
Okay.
I don't know what it's like.
Okay.
Anything, right?
Sure. Why not? Let's have some fun.
Water first, and then.
I'll drink all your coffee.
All right, let's get started. So thanks everybody for coming. It's my privilege to welcome Rachel Holladay to give her founding candidate talk here. She's currently a PhD candidate in the Electrical Engineering and Computer Science Department at MIT. She is advised by both Alberto Rodriguez and Tomas Susano Perez. She received her BS in Computer Science and Robotics from CMU. She is the recipient of a number of awards that she purposely didn't put in her bio, but I found them. So she received the Best Student Paper Award at RSS 2018 and is the recipient of an NSF GRFP. And her research focuses on long horizon, contact-rich manipulation tasks in everyday environments. And with that, I will hand it to you, Rachel.
Thanks, Bob. So thanks, I'm so happy to be here and to jump right in going off what Brad said. My goal is that I want my robots to be able to cook dinner in the home, to clean up messy classrooms, and to pack supplies in hospitals. And to think about what our robot needs to do in order to accomplish those types of tasks, let's consider asking a robot to, for example, cook stir fry, and we'll think about the first step in the recipe, which is to chop up vegetables. So here I have my robot, I have a knife for chopping and cucumbers. I like cucumbers in my stir fry. So we might think about what does it take for a robot to accomplish this task? I'm gonna hide my Zoom. Okay, hopefully I don't regret that. So thinking about, what does it take to get a robot to accomplish this task? And I'm going to frame this is that first the robot has to solve for what is the sequence of actions, or rather game plan or strategy that it needs to accomplish this task. And if we're chopping up a cucumber or we're cutting a cucumber, then a valid initial strategy might be that we'll ask the robot to grasp the knife, to move the knife to the cucumber, and to slice it. Now, for the robot to actually execute this in the real world, it has to solve for the discrete and continuous action parameters for each of these actions. So for example, if we want to grasp the knife, we have to solve for how do we grasp the knife in a way that we can actually reach and use to slice the cucumber? How do we move our robot's arm to that grasp position without colliding with anything? If we're thinking about slicing a cucumber, we can think about what forces do we need the robot to exert and what arm motions achieve those forces. And this is just a small subset of the things the robot needs to solve for. And as I mentioned, many of these parameters are continuous. There are a continuous number of ways you could grasp an object or trajectories that move through the world. But given this, what we can ask is this a viable strategy for the robot to accomplish the task? Could it find a satisfying set of parameters and actually accomplish the task in this environment? I'm going to lead the witness slightly and say that in this case, it would not succeed because if we go to cut the cucumber, nothing is holding it in place and that it's likely to roll around. Not only is that maybe a low-key dangerous, we're unlikely to succeed at the task. And so in this case, I'm going to declare that this would be a failure and that our robot needs to find a new strategy to accomplish the task, namely one that holds the cucumber in place. And so this is a particularly odd kitchen where we have a vise. And so we could secure the cucumber with the vise. You don't know what my kitchen is like, this could be valid. And so you can imagine that the robot's action sequence could now be it's going to grasp the cucumber, place the cucumber in the vise, close the vise, and then grasp the knife, move the knife to the cucumber, slice the cucumber. And like before, there are a lot of action parameters that we have to solve for. In addition to the ones I mentioned before, how do we grasp the cucumber? How do we move the cucumber to the vise? Where do we place the cucumber within the vise? But given all this in this new strategy, we can ask that same question from before, which is this going to succeed in this environment? Well, there's this red object that's sitting on top of the device. It's kind of taking up space and blocking the cucumber. And what this means concretely is that there does not exist a collision-free pose for the cucumber within the device. And so again, this strategy would not succeed. So the robot has to come up with a new strategy. And let's say it now decides it's going to grasp the red block, move it anywhere. It just has to be out of the way. And then once it's done that, it can continue with the strategy from before. Now, again, I ask the same question, will this succeed? As fun as this game is, I'm only going to play it for so long. So in this case, yes, the robot can plan and execute a series of motions. It's first going to move that red object out of the way. Once it's done that, it can go over and grasp the cucumber and place it within the vice. Planning for the vice is part of the system, so it's the robot's responsibility. And once it's done that, it can go grasp the knife. Oh, this gets people. It is a real knife. We're not doing toys. I intend to actually cook. That sometimes scares people. But okay, given that, good job, robot. We were able to slice the cucumber. And I frame that as that the robot was solving for a sequence of actions and the parameters of those actions. And those two influenced each other and were also influenced by constraints in the environment. Now, I'm really happy that my robot was able to solve this task in this environment. But I want my robot to be able to solve many tasks in many different environments. And so what I really want is I want my robot's behavior to be able to generalize. And I would argue, in order to get to this generalization, our robot has to do some type of reasoning like we did, in the sense that it has to reason over this hybrid combinatorial decision space where there are constraints based off the task and the environment. I want to tell my robot what to do. I don't want to tell it how to do it. That if I had to specify to my robot exactly what it had to do in each environment, that would get pretty laborious. And in a similar vein, if we took a strategy like behavior cloning, that would struggle to kind of aggressively generalize in the way that I want my robots to. So because I have this motivation for generalization, the majority of this, we're going to take a model-based approach. It'll be the robot's responsibility to reason over its constraints, given models of its task in an environment. Now, those models could come from engineering mechanics and be analytical, or they could be data-driven and learned. All of the above works as long as it fits within a framework that composes. Now, this idea of I want to solve a combinatorial hybrid decision-making problem for my robot, and I'm taking a model-based approach, fits within this category of task and motion planning, or TAMP. Now, my colleagues and I wrote a survey paper a few years back, and while there's been a lot of lovely work in task and motion planning, the overwhelming majority, with one limited exception, has been focused on enabling robots to reason over constraints relating to geometry. Let me hide this. And what I mean by that is that the robot is checking constraints like, is that motion collision free? Is that object reachable? Is that placement free? Now, this is still a very hard problem. If you have lots of objects, or you're operating on a long horizon, or you're dealing with cluttered spaces, it's still a hard problem to solve for. We saw how that red object in the way forced us to change our plan. But I would argue that this is fundamentally limiting if the only thing we're reasoning over is geometry. This is why if you have any familiarity with task and motion planning, you may associate it with just pick and place tasks. And this is because, if we think back to the tasks that I started the talk off with, that in order to accomplish these tasks, this requires the robot to reason over constraints relating to both geometry and physics, right? The fact that we were exerting force through the knife forced us, pun intended, to relocate our object to somewhere where we're secured. Likewise, you can imagine if you had a robot that was rolling out dough, or dynamically swinging a hammer, or packing supplies and deforming them, that all of these would impact the robot's decision-making. This is why my research is focused on proposing models and algorithms that enable reasoning over geometry and physics to accomplish long-horizon robot manipulation tasks. Now, I've worked on several thrusts in this area, and I'll say all of it is motivated by, grounded, and deployed on real robots. To me, that's the test of, does something actually work? And it's also where all of the joy and definitely none of the pain comes from. But today, we're going to focus on two specific areas, which is enabling robots to reason over forces. We've already motivated that slightly. And then thinking about how we can get robots to make robust decisions in the face of uncertainty, because if our robots are operating in the real world, they have to deal with uncertainty. And before we dive in, any questions so far on kind of motivation and setup? Okay, let's get to the fun stuff. So I want to think about how we can enable robots to reason over tasks that require exerting force. And the kind of game plan, so everyone's situated, is that first we're going to think about how exerting forces impacts our robots' decision-making, how we can capture that within a constraint, and model it, and then how we can integrate that constraint into an existing state-of-the-art task and motion planning framework in order to enable planning. And the example task that we're going to use throughout this part of the talk is the idea of asking a robot to open a childproof push-twist medicine bottle. It's a medicine bottle where in order to open it, the robot has to both push down on the cap and twist. If we put a frame on there, we can think of it as that you have to exert a downward force and torque about Z. For now, we're going to assume that these quantities are given. Later on in the talk, we'll relax that assumption. Think about the robot accomplishing this task. Here's a quick video. The robot exerts this push twist action. And then once it's done that, it can open the cap. I have no robot to do that for my bottle today. Sad. Okay, so the robot was exerting a force and torque while it was doing that push twist action. And I'm going to argue that the need to exert a force and torque or a wrench impacts the robot's decision making in two ways. The first of which we already saw in the cucumber cutting example, and that is that if we're exerting a force and torque on an object, we have to hold it still. For example, here, if nothing is holding the bottle still, then it's going to move with respect to the table. It actually slips, and we're not able to successfully complete the task. The reason why that didn't happen in the first video I showed you is that the bottle is actually on a red mat that has a high friction coefficient, and this provides enough grip to hold the bottle in place. So what I'll say is that the system, whether it be the environment, the device, another robot, needs to hold or secure, or what I'll say is fixture the object in place. The second constraint on our planning is that the robot has to be strong enough to accomplish the task. Now, what do I mean by this? To answer it, we're going to do a slight technical dive. So I think of the entire system, the robot, the bottle, the table, as a kinematic chain that is composed of a series of joints. And some of those joints are robot joints, and some of those are what I'll call frictional joints formed via contact. For example, the robot's grasp on the bottle. And the constraint that needs to be true in order for us to plan, in order for the robot to be strong enough, is that in the face of the exerted force and torque, each of the joints needs to be able to resist that force and torque. Each of them needs to be able to be held or stable. So what we're going to do is we're going to mathematically model the amount of force and torque each joint can resist. And we'll say if it can resist it, colloquially that the joint is stable. And if all of our joints are stable, we'll say that our chain is stable and our constraint is satisfied. So we're going to start off with the more straightforward case, which is thinking about what does it mean for a robot joint to be strong enough? Well, robots are limited in the amount of torque they can exert. They have torque limits. Breaking this joint would correspond to hitting a torque fault, or when it's a very sad noise, we want to avoid that. So we want to model, are we within the robot's torque limits? So what we're going to do is take the exerted force torque wrench, rigid body transformation into the frame of the hand. And then once it's in the frame of the hand, we have to transform it into torques at the joint. Now, in order to do this transformation, we're going to use what's called the manipulator Jacobian. So you take the forward kinematics of a robot and differentiate it with respect to time. You get the manipulator Jacobian. It maps joint velocities to end effector velocities, and beautifully, I personally think, the transpose of the Jacobian, which is what we have here, maps wrenches or force and torque at the end effector to torques of the joint, which is exactly what we're looking for. I'll note the manipulator Jacobian is parameterized by our joint angles, our configuration Q. And intuitively, you can think that makes sense. That you think about your own arms, sorry, not your own robot arms, that different configurations might allow you to resist more or less force, and our configuration dependent Jacobian is capturing that. So once we have transformed into torques at the joint, we can compare that to our robot's torque limits, which we assume are known. And if we're within our robot's torque limits, then our constraint is satisfied, and we can check this for all of our joints, or all of our robot joints. So this is the more straightforward case, I'd argue. We can also think about what does it mean for our frictional joints to be strong enough? Well, for our frictional joints to break, what I'll say is that means that the two objects would move relative to each other. So our two frictional joints that we have here are the robot's grasp on the bottle, as I already mentioned, and the bottle's contact with the table. And so we saw a case where the joint between the bottle and the table broke when the bottle slid relative to the table. And so we want to express how much force and torque each of these frictional joints can resist. To model this, I'll observe that both of these joints are what's called planar joints. And what I mean by that is if we look at, for example, the joint between the bottle and the table, in 3 dimensions, the object cannot move due to non-penetration limits. As because we are dealing with rigid bodies, the bottle cannot rotate into or go into the table. And so we'll assume in these three directions that we can resist an infinite amount of force and torque due to non-penetration limits. In the other three dimensions, we can move, and in fact, we've already seen a case where it did, and what prevents motion in these three dimensions is friction. And so the question becomes, how much friction do we have for these types of joints? Well, the amount of frictional support given by a contact is quantified by something called the limit surface. And because we're dealing with planar contact, there are two possible construction methods: the ellipsoidal approximation and the generalized friction cone. And which is appropriate depends on the type of contact that you're making. Now, to understand the limit surface a little bit better, let's dive into a bit the ellipsoidal approximation. So if you have a circular patch contact in a uniform pressure distribution, then the amount of frictional support given by a planar contact can be represented by an ellipse. And this ellipse is basically the set of frictional wrenches that this contact provides. And so thinking about this a bit concretely, you can imagine if this contact is experiencing an external force and torque, for example, the wrench represented in green here, if that exerted wrench is within the boundary of the ellipsoid, then we can say we have enough frictional support to resist that exerted wrench, and our contact will not move. This is good for us because this means that our constraint is satisfied. If we have an external wrench like the one given in red, where this exceeds the boundary of the ellipsoid, then we can say that our external wrench overpowers our frictional support and our objects are going to move relative to each other. Now, how they move is actually well characterized, but we're not going to use that in this context. We're just going to say that it is bad because our constraint is broken. Now, this ellipse lives in 3D and it's parameterized by this matrix A. For isotropic friction, this A has a few parameters. It's got the grasping force N, the friction coefficient mu, the area of contact R, and integration constant C. For now, we're going to assume that all of those quantities are known, but we're going to relax that assumption later on in the talk. So summarizing this, here in order to evaluate a constraint with respect to the limit surface, do a rigid body transformation into the frame of the hand, and then evaluate is that a wrench within the boundary of the ellipsoid. And because different graphs lead to different rigid body transformations, one graph may be stable when another is not. And so in evaluating our planar joints, our frictional joints due to contact, we're going to use a combination of kinematics and friction. And so bringing this all together, for each of our different joint types, we have a way of evaluating if the constraint is satisfied, if our joint is strong enough. And you might have guessed, because we saw it before, that here our frictional joint between the bottle and the table is not satisfied. And we can see that our models reflect that, in fact, that the exerted wrench exceeds the boundary of the limit surface. In this case, what we'd want our robot to do is to find a new strategy that constructs a new kinematic chain with a different series of joints that are stable in this case. Here, by using a high friction surface, that actually expands the boundary of the ellipse, and now we're stable. So summarizing from this, here we define what are the constraints that impact our robot's decision-making as a result of needing to exert force. And then we capture that within our forceful kinematic chain model. And while I talk through a couple different joint types and a couple of different models, you can imagine swapping in different models and joint types. For example, there is a 6D version of the limit surface if you are so inclined. Questions about this so far? Yeah.
Why don't you press down? Is that also an option? The force down force, or are you looking just at the torques?
Force and torque. So it's the downward force and the torque.
And you couldn't press hard enough?
Not in the robot would not be strong enough to press down because we're using, it's going to be a very specific answer, but we're using Cartesian impedance control. And for that robot, you cannot exert more than 20 newtons that way, and it would not be enough to make it stable. Okay. Although it does sample for that to check. Yes, if you have a strong enough robot, you can just power it through. Although we're not modeling whether you crack the bottle in half, which would maybe start to be a constraint. Great, other questions? Okay, we'll keep going. So now let's think about how we can integrate this within the context of planning. And to do that, I'm going to make concrete some of the things that I started the talk off with. And the first of which is that I've been talking about planning sequences of actions. I didn't define what I meant by actions, and all of you were very polite. No one called me out on it, but I would like to define that now. So when I say action, what I mean is a parameterized controller. We have some controller that we're executing on the robot and has parameters. For example, you can imagine we have a place action and is parameterized by things like the initial robot configuration, the placement pose, the grasp. And then in this case, it runs a combination of a joint space and a grasp controller. Now, given our controller, we're going to characterize our action by two things. And that's what's called preconditions and effects. Preconditions are what are the requirements or what needs to be true about the state of the world in order to execute your controller. For example, we might imagine a precondition to your place action is that wherever you're placing has to be available, has to be collision free. And then we have effects, which are what are the resulting changes to the world as a result of running your controller. So for example, an effect of executing the place action is that we're no longer grasping the object. And this is given in PDL, which is program domain description language. Now, this is one action. We can imagine defining kind of a whole set of actions. Here's the move action, and here's one of the push twist actions. And I want to call special attention to the push twist action because it's one that exerts a force and a torque. And so what we say is that a precondition to executing this action is that the forceful kinematic chain throughout this action that constraint has to be satisfied. And so that is how the constraint is integrated in, is that for any action that exerts force, the forceful kinematic chain constraint has to be satisfied as given in the precondition. I'll also note, although I already spoiled this, that in order to exert force, we're going to use a Cartesian impedance control. I'm happy to talk about this more at length. But given this set of actions, again, returning to the beginning of the talk, our planning problem is that we need to solve for a sequence of actions, the parameters of those actions, subject to constraints, and those constraints relate to both force and motion and are encoded in our actions, preconditions, and effects. And the way we're going to solve this, as I've kind of hinted throughout, is that we're going to use a task and motion planning framework. Now, specifically, I'm going to talk through the one that we use. It's state of the art. I think it also gives a good example for how these types of problems are solved in general, and it's called Pivotal Stream. So in order to use this framework, you have to specify a series of what's called streams. That is where the name comes from. So streams are just functions, and they can serve two roles. First is that they can generate possible instantiations of your action parameters. Because many of our parameters are continuous, you can think of these as samplers. So for example, you could have a function that given an object samples possible grasps, samples possible forces. You can also have streams that sample more complex things. For example, ones that sample possible trajectories that themselves run collision-free motion planars, so planars are called planars, or a stream that samples possible impedance parameters. In addition to generating possible instantiations of our action parameters, your streams can also evaluate constraints on your parameters. So for example, we have streams that check our forceful kinematic chain constraint and streams that check, is a trajectory collision free. Now, these are functions. Within them, you kind of implement them however you like. So again, you can use analytical models, you can use learned models, you can use a combination, kind of all of it works. I also want to highlight that in defining a new domain or a new problem class, like enabling robots to exert force, the majority of the work goes into specifying these streams. And you can think that's because this is where all of the implementation details are. This is where all the kind of the actual implementation goo goes. And for me, this also highlights an important point, which is that task and motion planning frameworks, they're really a computational framework of like putting together different planners and different solvers. And so there's still interesting questions of, what are those pieces? It doesn't get you away from solving those fundamental questions. So given these streams, we can run these streams to generate possible instantiations of our action parameters. And we take that along with our actions, our start state and our goal state, and we hand that off to a PDDL planner. This is a domain-independent discrete planner. We specifically use fast downward. And this planner is going to search for possible action sequences, what are those sequences of actions. And then Pivotal Stream is going to check, given the samples of our parameters that we have, can we have a satisfying assignment of those parameters for that particular action sequence? And it's basically going to keep looping, doing this combination of sampling and searching. There are details in paper about how this is done intelligently. But algorithmically, this is kind of capturing that reasoning that we showed off at the beginning of the talk of kind of sampling and searching and checking, do we satisfy our constraints? It's going to keep doing that until it outputs a plan. And a plan in this case is a sequence of parameterized actions. So here it's showing how it's solving that in the case of opening the childproof bottle. So again, it has to solve for what are the sequence of actions and what are the parameters of those actions. Now, this is the exact same planner that we used not only to solve this problem, but that cutting video that I showed you at the very beginning, because in this case, we specified a general purpose framework and kind of a general notion of the constraints. And so it can work for a variety of different tasks. Not only that, we can solve the same task in a variety of different scenarios. So here we have different bottles with different force requirements, we have different objects, different locations. In each case, the planner is solving for, given this environment, what is the strategy that I can use in order to solve the task? And so sometimes it uses a vice, sometimes it uses a tool, sometimes it has to relocate an object to a higher friction area, for example, there's not a vice or a second robot on the scene, and sometimes it uses the robot's palm. And to me, this is what is critical. My robot has to do this kind of decision-making in order to generalize to many different environments, so that it has to do that reasoning over, for this particular environment, how can I now solve it? I'll say in addition to these tasks, we also deploy this in the context of twisting a nut on a bolt. I will apologize, this is my only non-real robot video. It's because we did not have a 2-arm setup, but I do want to highlight that this framework can handle this type of uncoordinated bimanual manipulation just as easily. So here we saw how we integrated those force constraints into the state-of-the-art task and motion planning frameworks. Are there any questions about this so far? Yeah.
Does this framework is this framework limited to equipment, and how do you think you can address this problem if it is?
Equipment in terms of specific to the embodiment of the robot?
Yeah, like you said, some of them need 2 robot hands. Or maybe like the movement of the robot hand is limited or something like that.
So it's not limited to different hardware. And in fact, the last video I'll show at the end, we do consider a different robot hand. And so that's not a limitation. It does require that you know what your robot hardware is, and so that your planners have a notion for what your robot's capability is. But it's not inherently limited to different types of robots. Yeah.
I have 2 questions that are sort of related. So first one is, does PiddleStream do any sort of optimization? Does it see if
Yes, you if you wait 10 minutes, we will get there, because there is a notion of cost that we can handle.
and the second question is kind of related. Can you form an algebra from these actions, or is it just way too complicated to do that?
That is a fascinating question.
Uh-oh.
I do not know off the top of my head. It's not inherently clear that you could. I would say, yeah, it's not inherently clear that you could, because I don't think you could even adopt any of the kind of proofs that you might have from task planning, because now you have continuous elements that I assume would make everything just ungodly messy.
Do you at least know if there's like do you at least know if there's commutativity? Like you can always do one action for the other, or the other way around. Does it work, or does that break down?
I suspect that might be dependent on what your action set is, but I'd be hesitant to say that it is, because of the continuous elements might make things particularly messy and your constraints might not be universally satisfied. Apologies, I know this is an unsatisfying answer. Yes, should I be repeating the questions?
I think that would be helpful. But it's okay.
Yeah.
I do have one from the chat though.
Sure.
They want to know, does this framework generate the sequence of parameterized actions, or does it control parameters on scripted sequences?
No, it is generating the sequence.
Okay.
So the sequence of actions is not scripted. We would not want that, because that would be inherently limiting.
Thank you.
Cool. Okay. So for sake of time, we'll move on. We can keep doing more and more questions throughout. So, I highlighted within explaining the task and motion planning framework that kind of the heart of it is this idea of these streams. And we talked just now about kind of how to integrate force constraints on the task and motion planning level. But you might imagine that you may want your sub-planners to also be able to reason over force. And to kind of show an example of that, we're going to do a slight detour into the idea of in-hand manipulation, regrasping, and pushing. So here I want to place this T-shaped object, and the set of initially available graphs, because of the environment, does not intersect with the set of graphs that allow me to accomplish the task. Now, this is a somewhat contrived example, but I would argue the idea that you might have to change your grasp on an object comes up a lot. You can imagine if you're pulling a screwdriver out from a crowded tool bin, you might pull it out by the tip and then change to grasp the handle before you screw something. And so the idea of robots needing to re-grasp or change their grasp on an object has come up a lot within robotics. There's a lot of really beautiful work. Today, I want to look at one particular way a robot could change its grasp on an object, and that is by enabling a robot to leverage its environment. That specifically, it's going to change its grasp on the object by pushing against features in the world. And that by planning a sequence of pushes, it can change how it's grasping an object, in this case, to spell out some funny words. So the planning problem that it needs to solve here is that given an initial grasp and a final grasp, and locations in the world where it can push against. What the robot needs to solve for is where and how to push against in order to move from our initial grasp to our final grasp. And the kind of core constraint we need to solve for in this case is, given a specific pusher, what is the set of motions that I can achieve? Because pushing is underactuated, for a given pusher, there may be some motions that you can't achieve and some motions that you can. And so what we want to characterize is, for a given pusher in the world, what is the set of motions that are possible? Now, in 1986, my academic brother and grandfather, Matthew Mason, defined the motion cone as the set of feasible motions that a rigid body can follow under the action of a frictional push. Great, this is exactly what I said we wanted. Did my brother cover it? Well, so the motion cone was originally defined in the context of what's called horizontal pushing. You can imagine pushing an object on a table. But the video I showed, we were handling pushing what's called the vertical plane, where what was supporting the object was not a table, but the robot's grasp. In addition to the force of the pusher, we also have the force due to gravity. And so the contribution of this line of work was to extend the notion and construction of the motion cone to consider a broader set of planar environments where you have different support surfaces and different forces acting on the object. Now, what we're going for is, given a particular pusher, what is the set of feasible motions that we can achieve with that pusher? That's what's given in blue. That's our motion cone. Now, due to time in this talk, I'm not going to get into the details of the construction method, but going over it very quickly, essentially, we model what are the forces acting on the object. These are some of our old friends we've seen before, our limit surface, our generalized friction cone. We then combine and resolve these forces to get this, what is the set of possible forces, and then from that, what is the set of possible motions? And the set of possible motions is our motion cone. So motion within this cone corresponds to a motion that we can achieve using our pressure. Now, I won't get into the details, but we experimentally verified that this holds in practice with thousands and thousands of pushes in an instrumented setup. But if we return back to our planning problem, what we can now say is that, given an initial grasp, if we have a set of pushers in the world, that through our motion cone, each pusher defines what is a set of feasible motions. And what we can basically do is explore our space forward chaining these cones. We've taken kind of all the difficulties and underactuation of friction in physics and capture it within this closed form set. Here we're using specifically a sample-based motion planner called TRRT star. We can use it to find a sequence of pushes that move us from a start grasp to a final grasp. Now, return back to our video. Here we can see that first the robot pushes just directly to the side. But if I now swap out for slippier fingers, the robot plans to first push down to account for the fact that as it pushes to the side, gravity is going to cause it to slip. I'm putting the planning times on the in the corner here, and we're able to plan these sequences in fractions of a second. This is in contrast to a previous method that had to solve a complex inverse dynamics problem and took several seconds or even longer. We are able to handle non-convex objects, although we do assume that we know the object shape. So summarizing from this, here we extended this kind of fundamental notion of manipulation, the motion cone, to a broader set of planar tasks. The motion cone gives us a mapping of, given a pusher, a set of reachable motions, and we integrated this mapping in the context of a sample-based motion planning framework in order to handle in-hand manipulation. And if we think back to our stream conversation, we can imagine that this one planner is yet another subplanner within the context of our broader framework, kind of expanding our robot's dexterity. Questions on this before I move on? Yeah.
You think it will be an interesting question if you have a pusher on both sides?
So that is fine, as long as we know where the pushers are and their location and their geometry, then that's sufficient.
Oh yeah, I just feel like it will be a different sequence of actions, and sometimes it can be optimized. But I don't know if that's.
Yeah, we are assuming that you're making contact with only one pusher at a time.
Right.
If you were making contact with multiple pushers, then that would change the modeling because it's changing what are the forces acting on the object. So that would be a different case. Okay. So summarizing from this, here we saw how we can model the impact of forces in planning and kind of integrate that into our planning frameworks, both at the task and motion planning and the motion planning level. Throughout this, our robot has been having to solve for a variety of different constraints. And I want to now think about how I can ask my robot to both handle those constraints, while balancing the fact that I want it to be robust in the face of uncertainty. This is also going to enable us to relax some of the assumptions that I've highlighted throughout the talk thus far. In order to look at this, we're going to return back to our cutting example. So here, while there are a continuous number of ways to grasp the knife, for example's sake, we're going to consider 3 possible grasps on the knife. Now, given kind of all of the modeling that we just walked through, if we had a particular object that required a certain amount of force, we could evaluate if each of these grasps are suitable, if they're stable. And you might think that if we have an object that requires a low amount of force, like a peeled banana, that doesn't require a lot of force, that each of these grasps are sufficient. And in fact, they are. We're able to cut through the peeled banana with using all 3. But if we take an object that requires slightly more force, like an unpeeled banana, then this grasp that was only barely stable before, there's a lot of variation in bananas, let me tell you, that it might not succeed. While that middle grasp, it can still cut through the banana, and the grasp on the far side, it's easy peasy banana squeeze. But if we take an object that requires even more force, like our friend the cucumber, that these 2 grasps over here are not able to cut through the cucumber, but that grasp on the far side is able to. And if you remember the very first video I showed you, this might have been a hint of what was to come. Now, I will note that for each of these kind of food and grass combinations, I'm showing you 1 video. For each of the conditions, we did repeat this 10 to 15 times. On a personal level, it was a really weird week for me. Because, not to brag, I've had multiple meals in a row prepared for by a robot, just like not one a doctor would approve of. So I have to keep going in my research. But if you watched all of the dozens and dozens of videos, and you didn't watch me eating in the corner, you might come to the conclusion that this grasp on the far side is kind of doing quite well, and that it's able to cut through the most number of objects. And you might say, well, this is the best grasp, we should just go with this one. And on a more fundamental level, if this is the best grasp, then what are we doing all of this sampling and searching for? Shouldn't we just commit to this one? Not so fast. There's not one grasp to rule them all. First, because we're considering what is the strongest grasp for just the downward motion of the cutting action specifically. But to that more fundamental point, we have to deal with constraints related to both physics and geometry. So being strong enough isn't sufficient. And if you look at this graph, because of the geometry of the hand, it's the Frank and Mika hand, if anyone's familiar with it, that it's quite fat. And that you're only able to use this grasp without running into the table if your objects are elevated. That's why everything I've cut so far is on elevated cutting boards. Yes, I'm calling those cutting boards. And so you might imagine that in certain cases, depending on what you want to cut, you may want to make the trade-off of using this middle grasp that is strong enough, but maybe can get into a wider set of confined spaces. On the other hand, if you truly need to cut something that requires a lot of force, that the robot would then need to plan a sequence of actions that relocates the object to an area where you do have enough clearance to use this stronger grasp. And so I want my robots to be able to make these trade-offs, to think about how you can balance constraints while also being robust. And the way we're going to do that is we're going to frame robustness as a cost. And this goes back to the optimization question. So I'm going to take our forceful kinematic chain models, and for each of the physical parameters, I'm going to perturb them slightly. This is the amount of force that's required, the grasping area, the friction coefficient. We're going to perturb them. You can think of this as capturing a bounded amount of uncertainty. And across all of these perturbations, I'm going to count how many of them lead to the forceful kinematic chain constraint being satisfied. So this is going to give us a probability of stability given perturbations in our physical parameters. And if I take the negative log of this, then minimizing this corresponds to maximizing plan success likelihood. What I can say is I can assign this notion of robustness as the cost of my action. Within a framework like Potato Stream, we can use additive action costs, where the cost of a plan is the sum of the cost of an action. And then we can ask our planner to find a plan that is within some cost threshold. So you can think of this as being like how robust we want the plan to be. So this is optimizing for a very specific thing, this notion of wanting to optimize for robustness. You can imagine optimizing for other quantities. But why I like this is that now it enables the robot to both balance all of those kind of hard constraints while optimizing for what is the most robust choice in the given environment. So again, I don't want to specify to my robot what it has to do. I want it to be able to do that reasoning. Now here we're talking about robustness as a way to handle uncertainty. It's certainly not the only way to handle uncertainty, and we'll get back to that idea in a few slides. Questions about robustness so far? Okay. So summarizing from this, here we thought about how we can enable robots to kind of reason over geometry and physics for these long horizon manipulation tasks. And we specifically looked at reasoning over force and enabling robots to make robust decisions in the face of uncertainty. To me, I think this sets the stage for the foundations of the work I want my group to look at in the future. And specifically, I want to talk through a couple directions that I think are necessary to kind of push the field forward. How are we doing on time? Great. Okay, so I'm going to talk through kind of a couple specific directions and throughout that raise research questions. So the first of which is that I've said we're going to take a model-based approach, and the question always becomes, where do the models come from? So far in the things that I've showed you, either the models already existed or part of the contribution was writing down the model. But there are cases where I think that is a less reasonable assumption. So if we think about dynamic actions, moving out of quasi-static land, modeling dynamic actions is harder to do efficiently. If we think about objects that have kind of weird levels of deformation, like cardboard, or my favorite example, which is opening a key ring or pulling it open, or even scrubbing a pot and knowing how much force you need in order to get it clean, I think here it's less reasonable to think that we're going to have analytical models. I don't think it's necessary. And to me, this is a great example for when you would want to incorporate learned models. Now, I don't think it's necessary that our learned models need to capture all of the dynamics of the world. And only the question is, what do we need to capture in order to do that is sufficient for robust decision making? To me, also, leveraging learned models is an attractive way of combining planning and learning, because you can use learning to capture the kind of difficult dynamics of the world while still getting the kind of generalization and flexibility of the framework of planning. Alongside models, I introduced robust planning as one way to handle uncertainty, and we were really dealing with epistemic uncertainty in our action parameters. But as you have more complex models, what robust planning looks like, I think, has to change. Additionally, I want to imbue my robots with the ability to handle uncertainty in a variety of different ways. So yes, sometimes that'll look like robust planning, but sometimes that'll look like, taking cautious actions or doing information gathering actions and planning in belief space. And I think one kind of critical way to handle uncertainty is to integrate in more reactivity. So for all the videos that I have shown you thus far, the individual actions were closed loop. That's very important. But the overall action execution was open loop. If a nefarious human kind of ran in the middle and knocked something out of the way, we wouldn't be able to handle that. And I think integrating reactivity is an important way for handling uncertainty. I'm going to show that in the context of a very simple example of some work we've started on. So here the robot is actually cleaning up after itself, a rare thing. And it's going to be putting the silverware back. And the difficult part of this task is actually opening and closing the cabinet, because we do not know how much force is required. Now, in this case, the cabinet was fairly light and things were going kind of as expected. But if we now consider a heavier cabinet, what the robot is going to do is incrementally exert more and more force. And then once it realizes from its configuration that it can't exert the necessary force, it's going to replan, admittedly very naively, it replans from scratch on how it can open the cabinet. Now it's updated its estimate of how much force is required. So this is a very initial step of how to handle uncertainty with reactivity. I think there are a lot of deeper questions here about where we need to be reactive and at what level, and also how to integrate in reactivity with other ways to handle uncertainty, like, again, robust planning and information gathering actions. Now, if we think about where do models come from in dealing with uncertainty, I think a domain in which both of those come up a lot is in the idea of plastic deformation. Now, given that I said I want my robots to cook dinner, it might not be a surprise that I want my robots to do cutting. And in fact, cutting has been an illustrated example throughout this entire talk. But I think we really only scratched the surface of the cucumber. And in addition to there being a lot of practical applications, I think plastic deformation raises a lot of interesting deep research questions. I'm going to illustrate a few of them. One is that in all of the cutting we've done so far, you may or may not have noticed that we're approximating the objects as rigid, and that we're not dealing with objects that deform. In contrast, if you're dealing with a tomato, as you operate on it, it's going to squish and move. And there's questions of, how do we continue to act on that? In addition, we were not dealing with the fact that the objects were heterogeneous, but for a lot of objects, dealing with the heterogeneity of the object you're cutting through is critical. going back to a point I made with respect to models, I don't think it's critical that we have to exactly model how a tomato deforms. I think the question is, what do we need to model, again, in order to enable decision making? Furthermore, I said I want my robots to cut vegetables, and then I showed it doing exactly one slice, and the video stopped. That's not how anyone does cooking. For a lot of these actions, it's a series of repeated motions. And so I think there's questions of, not only how do we integrate those feedback loops and do them reactively, but I don't think we want to plan slice 1, slice 2, slice 3. I think we kind of want to be able to plan actions in bulk. And for that, I think we can take inspiration from generalized planning in the task planning community and multi-query planning from the motion planning community. Additionally, if we're doing this plastic deformation, we as roboticists really love to factor the world in terms of objects. But as we operate on these, it goes from an object to half an object to pieces to smaller pieces to granular media. And to what extent do we need to capture those state changes, and how can we continue to manipulate an object as it becomes less and less an object? Well, I've been saying cutting. I hope maybe you get the sense that I'm interested in kind of cutting in the general sense. So how can I enable my robot to peel, slice, dice, chop, pare, all of those kinds of verbs? And how do I imbue my robot with this kind of rich action space? I think there are questions of kind of what of these actions can we learn? And also, can we use kind of the wealth of information on the web from recipes to serve as guidance for this large state space? This is thinking about cutting and all the different types of plastic deformation in terms of one set of actions. But I really want my robots to operate over long horizons, right? I said I want my robots to cook dinner and to clean rooms. And for that, we've got to get our robots to operate over longer and longer horizons. And I think to do that, we need to leverage ideas of hierarchy, borrowing from task and motion planning. And I mean that in 2 ways. The first of which is I introduced task and motion planning as that we're planning for a sequence of actions and the parameters of those actions. You can imagine if we get into longer horizons, it may make sense to add a level of that we need or planning for a sequence of subgoals. And those subgoals have sequences of actions to kind of decompose our task. Now here, I don't think it's necessary that we need to plan what are the parameters for all of our actions, for all of our subgoals before we start acting. But it's the question of what are the fundamental constraints. As a concrete example of this, if I want my robots to make cookie dough, which I deeply want, I don't think before the robot starts acting, it needs to plan for what is the joint angles in order to crack the egg. But it should make sure that it has access to eggs, or those are going to be kind of gross. And so what are the kind of fundamental constraints that a robot has to consider? And what are the things that maybe you can do on the fly or reactively? I talked about reactivity in the context of handling uncertainty, but I think it's also a powerful tool in the context of thinking over longer and longer horizons. The second way I can think about this is that this notion of what is a subgoal versus what is an action is actually very fluid. And argue if you have more complex subplanners and you have more complex actions, that actually eases the planning problem. I think there are interesting questions of, how can we combine more complex and rich controllers into these types of frameworks, including ones that are perhaps more reactive. Lastly, another way that you could imagine gaining dexterity is by thinking about dexterity coming from hardware. Throughout all of this, I've assumed that our robot is fixed. It's been kind of the same robot throughout, but I think there are a lot of interesting questions if you think about co-designing your hardware and your software. And to illustrate that, I'm going to show off a recent collaboration. There's also going to be kind of a last set of robot videos that I want to show off. So this is a collaboration with Daniela Rosa's group, some students in her group. And here we built a robot hand that has 2 sets of conveyor belts in each of its fingers. And so running the conveyor belts in different directions, you can roll, pitch, or translate the object in hand. And so we integrated this into that same task and motion planning framework in the context of installing a light bulb. Now here, because of the packaging, we can only grasp the light bulb from the foot. And so once we've grasped it, we then re-grasp the object in hand, now by planning a series of belt motions in order to move the object. And then once we've done that, we need to install the light bulb within the socket. Now, ordinarily, this would be a complex set of repeated motions, like I mentioned for cutting. But we have conveyor belts for fingers, so this is super easy. We just keep running our conveyor belts. I promise they're running, even though it's a transparent object. You just sit around until, and I never time how long it's going, like they'll be so in this case, we had this cool piece within the context of a task motion planning framework, we added 2 actions and its corresponding samplers. And so there are questions of, whenever anyone shows me cool hardware, I think about like, how can I characterize it and integrate it within the context of this framework? It also has to be said, I think this shows off why collaboration is a great idea. Sorry. So summarizing everything up, I want my robots to be able to accomplish long horizon manipulation tasks. Think about the chores in your home and in your workspace. In order to accomplish these tasks, I think robots need to reason over geometry and physics. You have to consider the full richness of the world, what I'd say is the marvelous messiness and mechanics of manipulation. To me, work at this intersection is understudied but critical, and so it's a set of problems that I want to advocate for and solve. And in solving them, I typically propose models and algorithms that put the onus on the robot to do the reasoning, because to me that's what's required in order to get robots to generalize. And at the end of the day, I want my robots operating everywhere. With that, happy to take more questions. Thank you.
We have time for a couple of questions.
Okay.
Yeah, in connection especially with the problem of optimization and determination of optimal parameter values and so forth.
Yeah.
Could you say something about computational complexity? What happens when the number of goals scales up, the number of constraints scales up, the number of tasks scales up? How much computation we needed astronomically?
Yeah, I love this question. So the things that I showed you throughout this, I didn't give planning time for the task and motion planning stuff, but that can take anywhere from kind of 10 to 15 seconds to maybe a minute or two. But particularly because the planner that we're using is doing some level of rejection sampling, that as the spaces get more constrained or as you get longer horizon, the computation is going to go up. And I think from a scaling perspective, that is a real serious thing that we have to contend with. I think one way to get around that is to decompose into notions of hierarchy, of thinking about what do we have to plan for ahead of time and what can we plan on the fly. There's also a question of, the more informed your samplers are, which is the more information you insert, the easier you make your problem, but that also means you have to give more information. And so there's definitely deep questions about that. With respect to the optimization component, here we looked at optimization in the context of optimizing for robustness. To me, because I want my robots to actually work in the real world, that is perhaps more important than making them go faster or doing the shortest number of actions. But to be entirely frank, for a lot of these problems, satisficing is already so hard that optimizing is kind of another level. And also, if you're doing multi-step manipulation, what does it mean to be optimal is sometimes an unclear question. But you can, within this, a lot of the kind of subplanners that I was showing are sample-based. You can easily integrate in making your subplanners optimizers, and we've done that in the context of task motion planning. And then you might have individual components that themselves are optimized, even if the entire thing is not. So I don't know if that fully answers a couple different pieces. Okay, cool. Yeah.
Do we have a unified framework for modeling friction dynamics? You change, like sometimes use simulators, sometimes agents.
So in this case, we are always kind of using our analytical models, which means we have some notion of what the contact is like, so that we know what is the correct model to use. Should I be using limit surface or should I be using a generalized friction cone?
So you can put the MIT in a survey.
Yeah, so those were all using analytical models. Again, that has the limitation that it requires that you know what your you have a certain amount of privileged information. And so moving forward, there can be questions about how we get away from that. Although I do believe if you have enough information, using those models is really powerful because they're so compact and kind of well characterized. And they do actually well characterize the world. But yeah, we do assume privileged information in that case. For some of the dynamic manipulation that I'm doing currently, but only kind of briefly hinted towards, we are thinking about using simulators only because do not exist good analytical models. Yeah, up top. Nope, you. Hi.
Great talk. So how difficult it is to provide some sort of safety guarantees with these models, and also from the point of view like transparency within these models?
Yeah, so those are excellent questions, and none I'll touch upon. I think safety is a really interesting question. I assume you mean if a human is operating alongside?
Yeah, or even just guarantee of completion.
Yeah, there's not guarantee, for these planners, they kind of inherit the guarantees of their subplanners. So for a lot of these things, you have probabilistic completeness. So whether that's satisfying to you or not is a deeper question. But whether you have safety with respect to people, that's not currently integrated. And I think there is a question of how we can develop safe things. With respect to transparency, you do get the benefit of you will know what the action sequences are. You will not necessarily know why the robot came up with that action sequence if you want to understand why that is the way that it did. But because you have specified all of the actions, I think you do have a better understanding of how the constraints are being satisfied. So that's kind of hinting towards, but I think there are questions there. Other questions? Yeah.
I have a question related first. Thank you for your talk. With a framework like PDL Stream, is there a way to design your domain, your samplers to support efficient search over houses and trajectories and force programs in a way that avoids explosion?
Yeah, so I often think about combinatorial generalization as a benefit because it enables the robot to kind of consider a wide range of things. But this goes back to the first question of that you do have, the wider your search space, the more difficult the problem is. So I think you can get to that, attack that in kind of two ways. One of which is, again, if you have more informed information, then that can help. But I think this is actually another case where it makes sense to integrate planning and learning. A lot of the current learning frameworks, I don't know that I necessarily trust them to do the kind of long horizon planning. They've been shown to fail on a lot of the even simplest task planning benchmarks. But I think you could think about using learning and experience as a way to guide your search in order to reduce your search space and get some benefit that way. Especially for kind of these domains where we might have a lot of information or might have access to some level of demonstrations. And how can you leverage that?
I think we have time for one more question.
Go ahead.
Nobody else have questions?
It's all you.
Yeah, I was thinking like maybe reinforcement learning or like genetic algorithm could be really good options for like searching. I don't know if you have considered or not.
Yeah. So to me, those as a roboticist, I would like to have lots of different tools within my kind of grasp. I think there are cases where individual components, it might make sense that an action is kind of powered by reinforcement learning or genetic algorithm. I think they fit within the computational framework as individual components because there are some cases where they might do a better job in solving particular tasks. I think if you want to think about longer horizon planning, getting the amount of generalization would require a lot of data and search. And so I'd rather kind of apply those in the context of smaller problems and use kind of all of the tools within my toolkits.
You think about it small example?
Yeah, so I really, really don't want to have to write down the dynamics of cracking an egg. Like that just sounds awful, but I want that cookie dough. And so I think that is a case where either doing some kind of learning from demonstration or reinforcement learning. Although reinforcement learning where you have to crack a bunch of eggs is kind of a funny idea. But then it doesn't matter if you destroy it. That's the entire point. So I think those kinds of things where it's difficult to write down are attractive in kind of leveraging those types of tools.
All right, let's thank Rachel again.